Okay, now moving on to what the atom looks like. Okay, so Dalton is like the not the god. He is the like head of everything that came up with having to do with the atom. We use his research and his postulates or main themes for most of what we know about the atom, and then we kind of added on. Okay, so Dalton's laws, Dalton's theories are these 6 statements that each element is composed of tiny indestructible particles called atoms. All atoms of a given element are identical. The atoms of different elements are different and have different properties. Okay, so that makes sense. Most elements have different properties. Atoms cannot be created or destroyed. We already talked about that one. They can combine in simple whole number ratios to form compounds like H2O or H2O2. Atoms of the same elements may combine in more than one way to form different compounds. Okay, again, like H2O and H2O2. And atoms are the smallest unit of matter that can take part in a chemical reaction. Now, as we've learned things, there's actually a couple of caveats to some of these postulates. Okay. Now, I will say these postulates had overwhelming evidence. Okay. So a theory, right? We call these Dalton theory. Isn't something that's just a theory in the sense that you think of it in regular conversation. So if you say, I have a theory, usually in regular conversation, that means, well, I think this might be the reason. A theory in science actually has a lot of evidence behind it. You can't call it a theory unless you have tested it in multiple different ways, multiple different times. Okay, so theories in science are actually have overwhelming amounts of evidence behind them, and we can believe or trust in them. Okay, a law, on the other hand, is something that just states what is true. So we just had the law of definite proportions, says this is always true. Okay, a theory explains why that might be based on evidence. Okay, so theories do have a lot of evidence backing them. Okay, so anyway, what we've learned since Dalton's day, our atoms are actually made up of smaller particles. So they're not the smallest particles, right? There's protons, neutrons, and electrons. Neutrons and electrons. And if we go even further, and this is not part of this course, these are all made up of quarks, which are even smaller, and we don't know as much about them. Okay. All atoms have the same elements are actually not identical because they can have different masses, right? You can have hydrogen 1 or hydrogen 2, deuterium or tritium, that's H2 and H3. They actually have different masses and they have completely different properties. So they're not identical. They can have different masses or properties. Usually, one isotope is going to be radioactive and the other ones are not. So they can be a little bit different. Atoms do not always combine in simple whole number ratios. As we start to get into organic chemistry using larger molecules, I would say a small whole number ratio, we're like 2s and 3s, maybe 4s. But you can have things like glucose, C6, H12O6, right? Those are big numbers. I would not call that a small whole number ratio. Yeah, you could reduce this, but that's not what the molecule looks like. This is actually what the glucose molecule looks like. So we're going to have a lot of organic molecules that have much higher ratios. Okay. And then finally, there are actually forms of elements that have different structures. So for example, carbon. If I have pure carbon, not all samples of pure carbon have the same properties or structures. Carbon can exist as graphite. It can exist as diamond. It can exist as charcoal. These all have different structures and they are called allotropes. So you might have heard that word before in science class. An allotrope is just something, same substance making it up, just has a different structure. Okay, on to 2.2. How did we get to our current model of the atom? We found out after Dalton, it's not just atoms. You can actually go smaller, protons, neutrons, electrons, all of that. Okay, so after Dalton came J.J. Thomson, and he did what's called the cathode ray tube or cathode ray experiment. Cathode ray tube, that's what this is a picture of. Okay, and his was actually pretty simple. Essentially, he shot a cathode ray, kind of like a ray of electrons, essentially, through this. Essentially, he shot a beam of what we now know are electrons through this tube. And notice he's got a negative plate here and a positive plate. And you notice that it always bent or attracted toward the positive plate. So that meant there had to have been something there that was negative. So essentially, he discovered the electron and the fact that it is negatively charged. Okay, so he's like, oh, there's a negatively charged particle within the atom. And so even if it was something going through, it was going to have a negative charge in there because it always attracted to the positive. Okay. At a similar time, Robert Millikan actually did the oil drop experiment, and he discovered the actual charge and the mass of an electron. This is kind of what that looks like. And I did link a video here. I'm not going to show it on here as though. Okay, so he found the charge and mass of the electron. Okay, so now we know the charge is negative. He actually found the value of the charge, like it's negative a certain number of coulombs, and that it has a very small mass. But he was able to do that with the oil droplet experiment. Okay, and then came along a lot of radioactive experiments, right? You've probably heard of Marie Curie and Pierre Curie. There are a few with Rutherford as well, but they found that there are radioactive atoms, right? We can get alpha, beta, gamma particles. They have different properties. They're all damaging in some way, shape, or form. We will do a whole unit on nuclear chemistry later, but essentially they discovered that there's alpha, beta, and gamma particles, besides just the atoms that we have been talking about. All right, and then Rutherford actually did quite a bit. You probably have heard his name before, especially if you've taken a chemistry class. He did the gold foil experiment. Gold foil experiment. And essentially what he did was he shot a stream of alpha particles, okay, we were just talking about alpha particles, at a thin sheet of gold foil. And if we had an atom that had an evenly distributed negative and positive charge, this is what we would have expected to see. However, that is not what we saw. We actually saw the alpha particles being deflected at different angles. And what that meant is that, well, since some went through and some were deflected, there must have been some dense center, the nucleus, that actually deflected those alpha particles, because alpha particles are pretty big, and some went through, meaning that there had to have been empty space in those atoms as well. So essentially what this showed is that there must be a dense region, that was repelling the alpha particles, okay? Meaning he discovered the nucleus, and also that there's vast regions of empty space. The atom is mostly empty space, no charged particles in there at all. So since that was the case, now this became our model of the atom, right? This is not a very good model because it doesn't show us relatively the size of the nucleus versus the electrons. But now we have this dense positive center and the electrons on the outside. The last piece of the puzzle really for this model was James Chadwick. He discovered neutrons, okay, which change the mass. That's how we get different isotopes. And then we kind of ended up with this guy here. Now, remember that vast regions of empty space, so it actually looks a little bit different. This model is a little bit better.